Hi, everyone. In today's lecture, we're going to be talking about gases. So first, let's define what gases are. Usually elements in the first couple rows of the periodic table that have 5 or fewer atoms bonded together are going to be gases. Some of the diatomic elements that are gases are hydrogen, nitrogen, oxygen, fluorine, and chlorine. Most oxides of nonmetals are gases like carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, sulfur dioxide, sulfur trioxide. Those are all gases. And the noble gases, so everything in the far right column of the periodic table. And so the goal of this lecture is to describe the kinetic molecular theory of gases, and we're going to talk about units of measurement for various properties of gases. The kinetic molecular theory describes how gases behave from a particulate point of view. So if we think of gases as small particles, small molecules, the gas particles are moving around really quickly. They're bouncing off the walls of their container, they're bouncing into each other, and this constant force against the outside of the container puts a pressure on it. Okay, so gases have a pressure, there's a volume of the container, and these molecules have kinetic energy as they're flying around. And if you increase their temperature, they're going to fly around faster and have more kinetic energy. So the take-home message is gas molecules are really small particles. They fly in straight lines until they bounce into something. And this behavior will dictate a lot of their properties. So we can define 4 different characteristic properties of a gas. Pressure, abbreviated P, volume, abbreviated V, temperature, abbreviated with a T, and the amount of the gas, which we abbreviate as N, and the amount is in moles. And so pressure describes the force exerted on the walls of the container of a gas, and we use different units of measurement for pressure: atmospheres, millimeters of mercury, torr, pascals. We'll talk more about these a little bit later. Volume is the amount of space a gas occupies. How big is the container? And we measure that in liters or milliliters. Temperature, obviously, you guys know what temperature is. This determines the relative kinetic energy of the particles, how fast they're moving. We measure this in degrees Celsius or Kelvin. So all the equations we're going to use in this chapter, we're going to be using Kelvin. It's very important. And the amount of gas, basically how many molecules of gas are there in our sample. And we measure that in typically moles. So let's talk about each of these properties one by one. Volume. So volume is the amount of space that the gas occupies. How big is the container? Temperature, obviously, is the relative measure of the energy of the gas particles, right? Hotter temperature, they're moving more quickly, they have more energy. Colder temperature, they move slower, they have less energy. Now, pressure, maybe you guys have never thought about this, but we define pressure as force divided by area. And so for gases, pressure is the force that the particles exert on the walls of their container. And the area is going to be the size of the container, the surface area of it. Now, we measure pressure in different units depending on the situation. Millimeters of mercury, abbreviated mmHg. Remember, Hg is the elemental symbol for mercury. That's one of the older methods of measurement. Torr is another old school measurement. A more modern one is measurements of atmospheres. And so 1 atmosphere is defined as the air pressure at ocean level on Earth. So atmospheric pressure. This is more useful for a lot of our chemistry calculations. In physics, they use pascals or kilopascals. In America, we use pounds per square inch. So pounds is the force, the square inch is the area. We abbreviate that as PSI. So most of your tires on your car, the measurements are in PSI, right? You have to have so many PSIs of air pressure in your tires. It's just a different unit. All of these are units of pressure, and there's conversions for going back and forth between each of these. Now, the original device to measure air pressure was called a barometer. And so the barometer was basically a glass tube that was sealed at the top, and it was filled with mercury and then flipped upside down in a dish of mercury. And so gravity makes the mercury in the tube want to fall out because it's sealed. Uh, it creates a vacuum. There's no air particles in there. And so gravity is trying to pull the mercury down, but the pressure of the air on Earth is pushing down on this open beaker of mercury. And so the air pressure forces the mercury back up the tube. And so the height of the mercury in this tube can go up or down depending on how much air pressure there is. And so at sea level, mercury rises about 760 millimeters up an inverted glass tube. And so millimeters of mercury literally refers to how high mercury rises in a barometer. We actually had a really cool barometer in the lab from like 100 years ago with liquid mercury in it, but the moving company broke it last year, so we don't have it anymore. But yeah, they still make barometers. They usually don't use mercury anymore, but any liquid will work. But with mercury specifically, it will rise 760 millimeters of mercury. So the definition of 1 atmosphere is 700 millimeters of mercury, right? Because atmospheric pressure, that's how high it goes. Now, the scientist who invented the barometer was named Dr. Torricelli. He's Italian. And so sometimes instead of calling it millimeters of mercury, in his honor, they call it torr, short for Torricelli. And so 1 torr is the same thing as a millimeter of mercury. And so 760 torr is the same thing as 760 millimeters of mercury, which is the same thing as 1 atmosphere. So atmospheric pressure is not constant on Earth. If you take a look at the Earth here, I'm going to do a really poor job of drawing Earth here. There's Florida, and there's North America and South America. Yeah, not too bad. So air particles on the Earth are really concentrated around the surface because of gravity. But as you get higher, the air particles become further and further apart. And so there's a high density of air molecules close to the surface of the planet, and there's fewer further away from the surface of the planet. And so the air pressure is higher closer to the surface, and there's less pressure as you go closer to outer space. And so the definition of 1 atmosphere is at ocean level, but if you're up at the top of a mountain, the air pressure is significantly less, right? And so air pressure on our planet varies with elevation. And you don't need to know any of you don't need to know any of these values, but this is a cool chart showing air pressure at various altitudes. I'm going to zoom it in so you can see it. At sea level, right? Atmospheric pressure is 760 millimeters of mercury. The lowest point on Earth is the Dead Sea in the Middle East, and it's 400 meters below sea level, and the air pressure is actually higher. It's 800 millimeters of mercury. LA is slightly above, right? So the air pressure is a little low. Vegas is 700 meters above sea level. The air pressure drops to 700 millimeters of mercury. Denver is about a mile above sea level, and the air pressure is only 630 millimeters of mercury. Mount Whitney, which is the tallest mountain in California, has an air pressure of 440, and then Mount Everest, the highest mountain on Earth, has air pressure of only 253 millimeters of mercury. So that's pretty significant, right? You know, comparing ocean level to the top of Mount Everest, there's a third of the air density up there, which is why people wear oxygen masks when they climb in the Himalayas, because every breath of air you take, you're only getting in 1/3 the amount of oxygen. So you have to take 3 breaths to get the same amount of oxygen into your muscles when you're climbing Mount Everest. So pretty crazy. Anyway, take home message is the higher up you go, the lower the air pressure. And the units we use for measuring air pressure vary. So the unit that we'll be using mostly is atmospheres, and we abbreviate that as ATM. We'll also be using millimeters of mercury, and there are 760 millimeters of mercury in 1 atmosphere. A torr is the same thing as a millimeter of mercury. We're not going to be using inches of mercury, but this is used sometimes in American measurements. Pounds per square inch is also used in American system. We probably won't use this in chemistry class, but just so you know, there's 14.7 pounds per square inch to 1 atmosphere. And then pascals and kilopascals are physics units, and 101,325 pascals is equivalent to 1 atmosphere. So these are some conversion factors. You don't need to memorize these. These will be given on the exam. So let's do a quick study check. What is 475 millimeters of mercury expressed in atmospheres? So they give you millimeters of mercury, and they want you to get to atmospheres. So let's start with the given number, 475 millimeters of mercury. We're going to use our conversion factor here, and there is 760 millimeters of mercury to 1 atmosphere. So 1 atmosphere is 760 millimeters of mercury. And so when you multiply that across, millimeters of mercury cancels. And we pull up a calculator. 475 divided by 760, I get 0.625 atmospheres. All right. Question 2, the pressure in a tire is 2 atmospheres. What is this pressure in millimeters of mercury? Well, let's start with the given, 2 ATMs. And we're going to use the same conversion factor, but we're going to flip it because we want atmospheres on the bottom, and we want millimeters of mercury on top. So there's 760 millimeters of mercury for every 1 atmosphere. Atmospheres cancels. So 2 times 760 equals 1520 millimeters of mercury. Okay. It looks like we did it right. So now that we've talked about these 4 properties of gases, let's look at an equation that relates all of these. So your book doesn't discuss this, but this is pretty much covered in every other chemistry textbook I've ever used. It's pretty important to know. This is called the ideal gas law. And so the equation states that the pressure of a gas multiplied by its volume is equal to the number of moles of the gas times the ideal gas constant R times temperature. Now, R is defined as 0.0821 liters times atmospheres over moles times Kelvin. And it's called the universal gas constant. Now, why do we call it a constant? Well, if we take that PV equals nRT and we rearrange it, we get pressure times volume divided by moles times temperature is equal to R. And this is true for any sample of a gas. If you have a little tiny balloon and you take the pressure in the balloon times the volume of the balloon divided by the moles of gas and the temperature, you get this value R, which is this number. If you had a bigger balloon and you took its pressure times volume divided by moles and temperature, you would end up with the same value. That's why we call it a constant, because it doesn't change. It doesn't matter what sample of gas we're talking about. A little sample, a big sample, any sample of gas, the pressure times the volume divided by the moles and the temperature is always equal to this value. It's a constant of our universe. And so this is useful when we're looking at changes in a gas. So if you have, let's say, a little balloon, right? And the initial conditions, right? Small balloon, cold temperature. You take its pressure and volume, moles and temperature, you get R. Well, if you change the conditions of that balloon, let's say you put some more gas in there, blow it up a little more, you heat it up, it gets bigger. Well, it would have new values for pressure, volume, moles, and temperature. But if you compared that ratio, you would still get the ideal gas constant because that never changes. And so we can derive this, which is called the combined gas law. And so the initial pressure, initial volume over the initial moles, initial temperature is going to be equal to the final pressure, final volume, final moles, and final temperature. So comparing two different conditions, you can set them equal to each other as long as they're in this ratio. So I will give you this equation on the exam, but this is the equation that we're going to be using to solve problems. And so we'll be revisiting this in the next lecture video and possibly also the ideal gas law. So ideal gas law will be given on exams, as will the combined gas law. So thanks for watching, and I will see you in the next video.